Alright, so let's start. Okay, so this is the last lecture. Um, Yesterday we talked about some applications of the free boson, and now I will forget the free boson. I want to go back to just the general formalism and general CFT. General discussion of a conformal field theory in two dimensions. So we started this in the third lecture. So remember, we discussed the fact that a CFT, you could think of it as a recipe to define and compute partition functions and correlation functions that are ratios of partition functions. And we saw that the first key ingredient, that's really by far probably the most important ingredient, was the stress tensor. The stress tensor, and we saw that it obeys a nice a particular transformation law under conformal maps, that it was transforming in this way. This way here is just follows from the fact that this is a field with conformal dimension 2, but then there's this anomalous term here that is extremely important, where we see that there's this number C that appears, that is the central charge, and the central charge was 1 for the free boson. In general, it can be other numbers. So we'll talk more about this today. But so again, so this is this is the sequel of lecture 3, if you want. So we are going to talk about, so have a glimpse of general 2D CFT formalism. We are going to go a little bit deeper into the formalism. We're going to talk about, in particular, about operator product expansions, about the algebraic perspective. So we see that conformal field theory has a Hilbert space, and there's an algebra acting on that Hilbert space, and it's important to understand the representations of that algebra. And I would like to end with minimal models, and if I have time, connection with RG fixed points of phase diagrams. So this is relatively standard. All of this for today is quite standard material. You would find it in any textbook on conformal field theory. So for instance, famous some textbooks on this. Of course, there's the Di Francesco, Mathieu, and Seneschal. This is the Big Yellow Book. Big Yellow Book. But then there are other books. There's the one by Giuseppe Musado. There is also the book by my former colleague Martin Henkel. So you find many different textbooks. So we'll go quite quickly over this material, since we have only 2 hours left in any case. So let's start with correlation functions. And yeah, one that I didn't mention that is really excellent are the lecture notes from Lesouche by Ginsberg. Ginsberg, Lesouche, 88. So it's old, but it's still an excellent reference that you find on the archive. Okay, so correlation functions. And let's discuss covariance under conformal maps. So, if we have again a domain, some domain U, and we have a map Z maps to W to say the upper half plane. Then if we put some operators here, phi1, phi2, phi3. So here those map to this, so some points here, phi1, phi2, phi3. Then if the operators are nice enough, then they will obey the following identity. So this is the correlation function on the left, so it's in the domain U. That's in the domain U. And this should be equal to the mod of the Jacobian times some number that is the to some exponent that is the scaling dimension of the field. Times this, and here I'm writing it for a 3-point function, but this would hold for any number of points. It's not specific to 3 points. Just taking 3 points as an example. Like this. So x phi is the scaling dimension of the field of phi. So and this relation holds basically if the operator is sufficiently local. So the most local operators in the theory will transform in this way. And if the operators transform this way, so this can be different operators, we can have phi1, phi2, phi3. So operators that transform this way, operators that satisfy this for any correlation function, they have a name. They are given a name in the theory because they're very important. They are called the primary operators or primary fields are called primary operators. And of course, not all operators in the theory can be primary. This is, we have already seen an example of an operator that is not primary. That was the stress tensor. But there are many other examples. One way to find examples of operators that do not transform in this way is just to consider derivatives. Obviously, if you take derivatives of this field, the derivative will act on the Jacobian, and then they will spoil this nice relation. So there's a certain set of operators in the theory that transform nicely, and these are the primary operators, and that's the second most important ingredient. It's the set of primary operators. And now, in general, in practice, most of the time, the primary operators, these are non-chiral fields, but they factorize into a chiral part and an anti-chiral part. That's usually the case, not always the case, but usually it is. Sometimes what happens is that it's not exactly a product, it's a sum of products, but fine. So let's to make things simple, let's just assume that this happens, and so then The point is that I can look at the chiral part and anti-chiral part separately, and under a conformal transformation like this, phi of z would transform as dw over dz to the delta to some number to an exponent that is delta phi of w, and delta phi is the conformal dimension. It's called the conformal dimension. There is also a delta bar phi associated to the field phi bar. Most of the time delta phi and delta phi bar are equal, but not always. And delta phi plus delta phi plus delta phi bar, this is what we have called so far x phi. So it's this sum of the two is the scaling dimension. If they are not equal, then the difference of the two tells you how the operator transforms under rotations. So it's like a nebular momentum in 2 dimensions, or if you want a spin of the operator. Good, so that's the second ingredient, it's the primary fields. Now, okay, so now let's look a bit at the a little bit more in details at 2, 3, and 4 point correlation, 2, 3, and 4 point correlation functions, correlations in the plane. Yes. No, I will use both words interchangeably. Yeah. Okay, and so for this we are going to use some of the material we had in the first lecture, namely special conformal transformation. So let's start with the 2-point function. So let's imagine we have our plane, complex plane C, and we put two operators, phi1, phi2. Phi1, phi2 at some position z1, z2. And just to lighten the notations, let's keep only the chiral part. Right? So we keep track only of the chiral parts. Okay, so according to this transformation law here, we have that phi 1 of z1. Okay, sorry. What I can always do is that I can always find a special conformal transformation or global conformal transformation that maps z1 to 1 and z2 to 0. Okay, so 1 is w of z1, z2 is w of 0, say. So I can always find a special conformal transformation that does this. And if I do this, then I get that phi of z1, phi of z2, phi1, sorry, phi of z2. This is given by the Jacobian of this transformation to the delta 1, here Jacobian at point z2, to the delta 2, times phi at position phi 1 at position 1 and phi 2 at position 0. Okay, I'm going to continue here. And now I can ask, okay, but let's plug the explicit form of this map W. But in fact, the map W is not unique, because you see I can choose any. There are several special conformal transformations that do the job. So for any omega, let me just for any omega in the complex plane, I can for any omega in in C, you see that this map is going to do what I am advertising here. So it's going to send Z1 to 1 and Z2 to 0. Okay, but if I plug that into the correlation function over there, then this tells me that phi1, phi2 of Z, this must be Z2 minus omega over Z1 minus omega times Z1 minus Z2 to the delta 1, and the same thing for where you exchange indices 1 and 2. Okay, and now you see that this is a problem because the whole discussion is still about this correlation function here. So it should not depend on what, this is the object we want to calculate, then we do something with it, and the result looks like it depends on what we are doing. But it's of course still the same object, it's always the same object, so it shouldn't depend on the specific special conformal transformation that we are choosing here. Okay, so in order, we see that this cannot depend on omega. So how is it possible that it does not depend on omega? So the only possibility is that phi1, that this is 0 if delta 1 is not equal to delta 2. And as long as delta 1 is equal to delta 2, then those factors that depend on omega, they will go away, so that's fine. And then we are left with the result that is some constant C times 1 over Z1 minus Z2 to the delta 1 plus delta 2. And this constant, it is conventional to take it as 1. So this is a choice here, there's a choice of normalization. There's a choice of normalization of the operator phi that is conventional, and it's the same choice that is made in absolutely all references on conformal field theory, so that's completely standard. So standard notation in conformal field theory is that the 2-point function is normalized so that you have this. And if the two operators do not have the same scaling dimension, then the 2-point function must vanish. So this is if delta 1 equals delta 2. What can be said about the 2-point function? Now, let's move on to the 3-point function. So similarly, if we look at the 3-point function, again we can find a special conformal transformation. So if we have 3 points phi1, phi2, phi3, and we can send 1 point to 0, 1 point to 1, and 1 point to infinity. Put infinity here. We can always choose a special conformal transformation that does this. This time, this special conformal transformation is unique. Because as we saw, there's a 6 real parameter family of such transformations, or 3 complex parameter family, and here we are fixing precisely 3 complex numbers because we are fixing the 3 positions of these 3 points. So that completely fixes the transformation, and then again using the transformation law of these primary operators, we find that this takes the following form. Phi1, phi2, phi3 must be equal to some constant that this time we cannot fix any longer because we already fixed the normalization. So some constant that we'll call phi C1, 2, 3, and then this is divided by Z1 minus Z2, sorry, let me try to write it clearly, Z1 minus Z2 times delta 1 plus delta 2 minus delta 3 times two terms that correspond to circular permutations of circular permutations of the indices of 1, 2, and 3. Okay, so there are three terms in this denominator. One is for 1, 2, one is for 2, 3, one is for 3, 1. So, okay, so we see at this point that special conformal transformations allow to fix the form of both 2-point functions and 3-point functions. Okay, and now we turn to 4-point functions. So if we do the same reasoning for 4-point functions, then so we have now 4 points, phi 1, phi 2, phi 3, phi 4. We can now find a special conformal transformation that will send, so to use the same convention as in the first lecture, we'd send 2 to 1, so that's, so Z2 goes here, Z3 goes here, alright, this is this map, Z maps to W of Z, and that's W of Z3, W of Z2. So Z3 maps to 0, Z2 maps to 1, and Z4 maps to infinity. And then we are left with 1 point, namely W of Z1, that we cannot fix, whose position we cannot fix. The position of this guy, we cannot do anything with it. So what is this W of Z1? Well, by definition that we saw in the first lecture, this W of Z1 is the cross ratio. So it's eta of Z1, Z2, Z3, Z4. Okay? Consequently, the 4-point function must be of the following form. So we pick these Jacobians. Let me write it as this. So we pick this product of Jacobians, dWj over dzj to the delta j, for j equals 1 to 4. Fine. But then there's something that we cannot get rid of, and that's f, some function f that we don't know of the cross ratio. And this in general we do not know, or it's not fixed. Not known. So this is not fixed solely by special conformal by invariance under special conformal transformations. You need to know more about the details of the theory to fix this 4-point function. Okay, so the important formulas here are the 2-point function, 3-point function, and 4-point function. So it's this. 2-point function, 3-point function, 4-point function. So we see that we see in particular that what has appeared here are these coefficients that fix the 3-point function, and turns out these coefficients are also very important data about the theory. They're called the structure constants. So they are also key data, key ingredients. So these coefficients, let's call them just the coefficients of the 3-point function. They are also and these depend on the 3 operators, right? So let's write it more explicitly: C phi 1, C phi 1, phi 2, phi 3. So these are numbers, and they are important data. Okay, so that's what can be discussed at this level of generality about the correlation functions. And next, to make more progress, we need to introduce the concept of operator product expansions. So operator product expansions, or OPEs. So definition. So, this is about looking at the behavior of operators or correlation functions when 2 operators are close to each other. So when 2 operators are close in space, that means if you're looking at the correlation function, say, of some operators here, phi, and then you have 2 operators, let's say phi 1, phi 2, that come really close to each other here, then viewed from the point of view of these operators here, these 2 should behave as one single operator, just because they are very close. So from far away, you cannot really distinguish them. Another way to think of this, if you want, is to say that each operator does something into your theory. I mean, you can think of your theory, for instance, as some sort of medium where you could have, for instance, like waves that propagate or something. That's just a picture. So each operator would, do something to the theory. And then if you have 2 operators that are very close to each other, then from far away you only see the signal that comes from both of them, but you cannot tell that there were 2 and where exactly they were. So that means, anyway, it's just some heuristic way of thinking about this, but this means that you expect to be allowed to do the following sort of expansion in all correlation functions. Something, let me write it as this, with some coefficient c, I, j, k. So when z is close to w, then you want to be able to replace the product phi I times phi j at position z and w by a single operator. Let's call it phi k. Phi k in general is different from phi I, phi j, and there's a sum over all these terms. So there are many different operators that can appear. Something like that, and just because of just the power counting, this has dimension delta I, this has dimension delta j, this has dimension delta k. Therefore, here you must have a denominator that is z minus w times, z minus w to some exponent, and this exponent has to be delta I plus delta k, delta I plus delta j minus delta k. Like this. Is it clear? No. No, so the sum is, here the sum is in principle over all possible operators in the theory, including, thank you for this question, so this sum includes primaries, but also non-primaries. So it's really all possible things in the theory. It includes everything. And especially non-primary fields. So there are a few primary fields. So in many theories that are interesting, there's a finite set of primaries. So very reduced number of primary fields, and then but then there are infinitely many other fields that are less local. And this sum includes everything. So especially this infinite series of non-primary operators. So there are a few primaries, but most of the terms here are not primary operators. But yes, well, I mean this delta k here is not necessarily the dimension of the primary. It can, yeah, but. So, okay, so at this point you might say, we have replaced this nice expression with two operators by a horrible sum with coefficients that we don't know and over an infinitely many terms. So why is this interesting? Well, of course it's interesting because then when z goes to w, so only some, there's a, you can arrange your sum or order it according to the scaling dimensions, so that you pick the most important part that will correspond to the smallest delta k, then the next part that will correspond to the next leading delta k, and so on. Right? So this is powerful only if you arrange your sum in a good way. What? Fusion rings. Yeah, this is the fusion rule. Yeah. I'm not gonna use that. Hmm? At this point, it's just anything. Yeah. Then usually when you talk about fusion rules, what you have in mind is you focus only on primaries, and you're interested only in the terms on this side that also involves primaries. But at this point, I'm not there yet. So. Okay, and this is valid. This identity, this type of identity, is valid when we insert it inside correlation functions. Okay, so this is valid inside correlation functions. So we can, for instance, use this to compute phi I, phi j of w, and then with a bunch of other phi's here, other operators, and we can use this expression to write our correlation functions in this way, times phi k of w, and then a bunch of other phi's. So then you see why this is potentially interesting, because here this is an endpoint function, and these are n-1 point functions. So in particular, you could try to, you see, this 4-point function that we've been talking about, that we don't know in general in principle, you could use this to express it in terms of 3-point functions that you know. Of course, to make this work, you need to know all these coefficients. Yes? Sorry? Here? Yeah, but I mean, it's because the 2 points here, these 2 points are Z and W, and they are viewed, they are very close to each other, so I can put W here, or I can put a Z. It will, I mean, perhaps it will reorganize a bit the terms, but I can just decide to fix one of the 2 points. Okay, so this expression again, it's useful only if you organize the series of terms here according to the scaling dimension. If you don't, then this is just an infinite sum and you don't know what to do with it. Okay, so now let's have just a quick look at from that perspective at the 3-point function again. Okay, so let's look back at the 3-point function. From the perspective of this operator product expansion. So we consider again phi1 of z1, phi2 of z2, phi3 of z3. And when we plug in this operator product expansion, we find that this is infinite sum over k of these coefficients z1 to k, z1 minus z divided by z1 minus z2 to the delta 1 plus delta 2 minus delta k, times some and then a bunch of 2-point functions that involve some field, some operator here, not necessarily primary, phi k, z2, and phi 3 of z3. Okay? And now let's send z1 to z2. When we send z1 to z2, there's one term here on that side that will dominate everything, and it's the one that has the smallest possible delta k. Which one, sorry? I mean, I literally did this now. I is 1, J is 2, Z is Z1, W is Z2, and then I just, it's this identity plugged in here. No, or did I make a mistake? Alright, so now we send Z1 to Z2, and there's a single term there's one term that blows up faster than all the other ones, and this is the one with the smallest possible delta k, right? On the other hand, the result should be equal to this when in this limit where z1 goes to z2. So from this result, we see that this should be equal to c, capital C, 1, 2, 3, divided by z1 minus z2 to the delta 1 plus delta 2 minus delta 3 times z2 minus z3 to the 2 delta 3. Okay? And so then we see that as a consequence, we must have that the term with the smallest possible scaling dimension must correspond to phi k. This operator here must be phi 3, so it must be a primary. It has to be, the leading term in here has to be a primary, has to come from a primary field, and on top of that, this constant that I've called C12k, this is in fact equal to this capital C123. So the coefficients that appear in the operator product expansion, at least for the primary operators, they are the coefficients of the 3-point function. Now, you can go further than this, but I'm not going to do it. I'm not going to do it in this lecture. But let me just tell you what you can tell. What's the structure of the other terms? So at this point, you see we understand what are these terms when phi k is a primary operator. We don't understand yet what they are when they are not when they are not primary operators. And this is a bit more complicated, so I will not do it. But let me just tell you what are the important facts. So in fact, one can show the following things. But this would require a little bit more machinery that we haven't seen yet. So the sum, so what one can show is that all operators phi k that appear in the OPE, operator product expansions, that are not primary, in fact, they come from a primary in the sense that essentially they are derivatives of primary. So they are associated to one specific primary. Each of them is associated to one primary. And you can think of them as derivatives. Essentially, they are derivatives of these primary. So they are just operators that fall in the same family as their primary ancestor, but they descend from it. Hence the terminology descendant. So they are derivatives of a primary, and these are called the descendants. They are called the descendants of the primary, of some primary, of the primary that they are attached to. And the other thing that you can show is that in this case, for descendants, for each descendant, this chalk is really annoying. So for each descendant, Cijk, so this coefficient Cijk can be expressed, can be computed in terms of the structure constant of the primary, or the structure constant of the primary. But in practice, this calculation is hard, and typically, I mean, you can design an algorithm that does it for you, but there's no in general closed formula So it's you can do it in principle, but it's difficult. But at least in principle, this means that if you know the 3-point function, again, 3-point function of the primary fields. So if you know the structure constants, so this is what I call structure constant. If you know the structure constants, then you know everything. Because you can use the operator product expansions. In principle, you know all the terms that show up in the expansion, and then you can reduce. If you are interested in a 6-point function, you can reduce to 5 points, 4 points, then 3 points, and for the 3-point functions, you know the result, and so. So is there a way to know? So that depends on the theory. We'll see some examples later where indeed we know them. Does it mean something about in terms of complexity of the theory? Yes, in the sense that the less primary fields, the smaller the theory, so the easiest in some sense. But that's it. So theories that have a finite number of primary fields, they are called rational conformal field theories. But there are many interesting theories that do not have a finite number of primary fields. For instance, than what we talked about at length so far. Yes, so what are the primary fields in the Gaussian free field? Hmm? Yes, the vertex operators are the primary fields. They are not the only ones. Also gradient H would also. So d phi and d bar phi bar, those are also primary fields. But otherwise the vertex operators. So this point splitted regularized exponentials, they are the primary fields. Okay, good. So that's for the operator product expansions. Now, okay, so at this point we have talked about the stress tensor, we've talked about these primary operators and their correlation functions. Now there's one thing that we need to make the whole thing consistent. We need to know somehow how the two are related, and this means we need to know correlation functions of the primary fields that also include the stress tensor. Or in other words, now that we have introduced the language of operator product expansions, we need the operator products expansion of the stress tensor with the other operators. Okay, so this has a name in the theory. These are called word identities. Uh, and so the those conformal word identities. So you've probably seen word identities in the more general context of field theories. So word identities associated to various symmetries, like just translation invariants. It's the same thing. Here it's just associated with general conformal invariants, and it's expressed in a different way because now that we have seen the operator products expansion, it turns out these word identities can be rephrased directly as in terms of the OP. So I will go very quickly over this. This is again, if you really want to dig more into this, this is something that is discussed at length in all the good references because it's an important point, but I will not insist too much on it. So the conformal word identities determine the operator product expansion of the stress tensor or holomorphic and anti-holomorphic components of the stress tensor, so T of Z, with the other fields, other operators. And in particular for primary field, for a primary field, the OPE reads as follows. So T of Z, phi of W, or Z, W. This is delta phi, so conformal dimension of the fields of the primary field phi over Z minus W to the 2 times phi of W plus 1 over Z minus Z, 1 over Z minus W d phi of Z W. That's the derivative here. And then there are other terms, but these other terms are not singular. So they have no poles. So, and this is the standard way to write operator product expansion. So, but the word identity, the way you derive this is, so you need to perturb the metric, write some integral, and then the integral you can turn into a contour integral, and then the contour integral you use Cauchy formula to analyze it, and you see that it depends only on the poles of the correlation functions in the end, and this is where it comes from. And this is also the reason why we do not care about the non-singular terms. It's because they do not play any role when you compute contour integrals. So again, I will not do this in detail. You can find this in any of the references that I gave earlier. So but anyway, this is a very important point, very central piece also of the theory, so let's put it here. So the stress tensor T and phi satisfy specific OPEs, which are very important in practice. Okay, I'll copy it here during the break, just so that we have it here. And for the stress tensor, so the stress tensor itself also satisfies an important operator product expansion with itself, which is the T of Z, T of W. This is 2 over Z minus W squared, T of W. You see this, you should identify with this term. It means the stress tensor has conformal dimension 2. That's the reason for this 2 here. Plus 1 over Z minus W times the derivative of the stress tensor. So if we had only that, this would mean, so if you are a trained conformal field theorist and you see an OPE like that, you see that it immediately means that the operator that shows up here or here, this is a primary field. But of course T is not primary, as I've emphasized, because there is this term that involves the Schwarzian derivative and central charge. And so this reflects on the operator product expansion as a more singular term that appears, that takes this form, C over 2 over Z minus W to the 4. So again, if once you have good training in these things, you immediately spot that this means this is a primary field with scaling dimension 2. This immediately means that you are talking about a theory with a central charge C here. So it's these operator product expansions are just a more convenient way to rephrase a number of facts about the symmetries of the theory, and they are very useful for practical calculations. So after the break, we'll see just a very little bit of this very quickly. So after the break, let's take the break now. So after the break, we'll talk about the Hilbert space of the conformal field theory, about the algebra that is acting on them on this Hilbert space, and I'll mention minimal models, and we'll see if we have time to talk quickly about our renormalization group fixed points. Any questions on this? Okay. Okay, so then let's have the break. Hello? Yes, okay. Okay, so we continue. Yeah, okay, so we have arrived at this, right? So in general, we have these ingredients. We have a stress tensor. We have a set of primary operators. This set of primary operators. Their 2-point function is fixed. The 3-point function is also fixed up to a constant that is an important data about the theory, the structure constants, and then everything, or not everything, but many things can be expressed simply as operator product expansions that typically look like this. So if you open a paper on conformal field theory, typically first equation in the paper will look like this. And again, if you are used to this, you immediately see that an OP like this means that this is a primer field with conformal dimension delta. You immediately see that this means that this is a CFT with center charge C, and so on. And why these operator product expansions are so important is because all the correlation functions that you compute for these chiral parts of the operators, they are meromorphic functions of the complex coordinate z, and so because they are meromorphic functions, they are usually specified by the poles. And so here you see the pole structure of these from these identities. You immediately see the pole structure that will show up when you compute correlation functions. Okay, so now let's discuss the algebraic. So the algebraic point of view, or the algebraic viewpoint, and we'll start with the Hilbert space. So there is a Hilbert space that is naturally attached to a conformal field theory, and this shows up as follows. So again, remember from lecture 3 that I said that a conformal field theory is a recipe to define and compute partition functions and correlation functions. And we were saying that you can, for instance, think of partition functions on surfaces like this, of this form. But what you would like to be able to do is predict the form of the partition function by doing things like surgery, right? So you would like, for instance, to be able to cut these surfaces and glue them together. Again, you see, just cut it, integrate out the degrees of freedom here, for instance, and then cut, and then glue them together to get the partition function that you were interested in the first place. So you would like to be able to do this kind of things. And the simplest, okay, so in general this is very complicated, but the simplest version of this is to try to glue a piece of the plane, namely a disk. So let's say we take a disk, and we would like to glue the disk, let's say a disk of radius 1, and we would like to get, for instance, partition functions or correlation functions in the plane by gluing this disk with the plane minus the disk. Okay, so this is plane minus the disk. This is the unit disk. Right, so D is the set of points Z with modulus of Z smaller than 1. Okay, so we would like to, look at a piece of the plane like this and the complement and be able to glue them together. We would like to be able to do this. So of course the partition function on the full complex plane, that's just by definition that's 1, so there's nothing to say. But if we start inserting operators, like if I put an operator here, for instance, phi 1, and another operator here, phi 2, and some other operators here, phi 3, phi 4. I would like to make sense of this operation of gluing the two things and getting a number out of it, and the number that I should get out of it should be the correlation function. Okay, so now let's think about a concrete example for a second. So let's think again about the Gaussian free field, just to make a bit more sense of this. And if we think about the Gaussian free field, what we see immediately is that if we want to do something like this, if we want to cut a piece of the surface, then we can integrate out the degrees of freedom inside, but we need to specify what are the degrees of freedom, namely h, the values of the H fields around the cut, right? So in the Gaussian free field, we would typically write something like this then. So this object, this thing where we are integrating out the degrees of freedom outside, but then we fix some configuration of H of the H field at let's around radius 1, but as a function of theta. This is angle theta. So we fix some configuration of H, we integrate out the degrees of freedom inside, and this, you see that then this will generate a sum over all. So what we are going to do is that we are going to say to define a state that we call 0. It's the vacuum. We'll call it the vacuum. So formally we can think of this as being the path integral over all configurations of H inside. So we integrate over all configurations of H inside the disk with the correct weight that is given by the exponential of our action inside the disk times states time states that correspond to these different configurations. Let me just write it properly. So h r equals 1, we integrate as a function of theta, like this. Okay, so we fixed some configuration of the H field around, we integrate out the degrees of freedom. This gives us a weight for each configuration of the H field around, and then we just take the linear combination of all of them, properly weighted, and this we call the vacuum. So this you should really think as, again, as this object, just this piece of the plane, with some degrees of freedom that are fluctuating around, where we have integrated everything outside. Okay, so this is what's called, in the literature, radial quantization. Just if you want to make the connection with some textbook. And so this is now the vacuum, but we can also define fields phi corresponding to the primary operators as what would happen to this picture if we were inserting the primary field phi at the origin. So we insert a field phi at the origin. We integrate out all the degrees of freedom inside the disk. This gives some weight to all the configurations along the circle, along the boundary, and this is a state. We define this as a state in the Hilbert space, in our Hilbert space. Okay, so now we have defined a few states: the vacuum, states associated to primary fields. But there are many others, infinitely many others that we can define. And these other states we can define by inserting the stress tensor inside the disk. So descendant states. So if we have one of these states, so we can also consider. So we can also consider states of this form. So we take our disk, we insert some primary operator here, phi, we insert some occurrences of the stress tensor at some point. Let's call this let's call this Z1, Z2, Z3, and so on. So we can include the stress tensor at different positions. And again, so this means that we look at the configurations of the fields of our theory along the boundary, and we just integrate out the degrees of freedom inside. This time having inserted those operators. So states like this are no longer primary. Do no longer correspond to a primary field. They are a linear superposition of what we call descendants, and it's not very convenient to work with these things, but there's a change of basis that makes it nicer. So it is convenient to work with the Fourier modes. It is convenient to work with the Fourier modes of the stress tensor. and those Fourier modes, so we typically write the T of Z, we write as an expansion like this, of Z minus 2 minus N Ln. So this is this convention for the labels in the sum is chosen so that you see this is a field with conformal dimension 2. This is something that with conformal dimension n, and then or minus n, sorry, and then this has conformal dimension 2 plus n, and so 2 plus n minus n, that's 2, so it matches this. That's the reason for this shift by 2 in the of the indices in the sum. Or equivalent, so this equivalently can also be written as Ln is contour integral, for instance, around the disk, around the circle of dz over 2 pi I, z to the n plus 1, t of z. Okay, so instead of looking just at insertions of the stress tensor, I can multiply, for instance, this one by z1 to the n plus 1, and then integrate it over a circular contour like this, and this will generate states. So if I do things like this, I would generate states of the form so of my primary field, and then I can insert more and more modes of the stress tensor, so I would get states of this form Ln1, Ln2, Ln3, Ln4, and so on to Lnp. Okay, and I can generate infinitely many of those, and this means that the Hilbert space of our theory usually is infinite dimensional. Okay, so if I continue my list of ingredients of the CFT, let me continue the list. So there's an algebraic perspective on this theory, algebraic perspective on CFT, which then includes so in that perspective there are states 0, and then states corresponding to the primary fields phi1, phi2. So these are all correspond to primary operators, and then for each primary operator you can generate descendants. So you can put L minus 1 0, L minus 1 squared 0, L minus 2 0, and you can order the descendants according to the total conformal dimension, which is given by the sum of all these indices. At this point I realize I forgot to say something. I'm going to say it in a minute. So okay, so you get for each primary state, you get a bunch of infinitely many descendants, and those things are called conformal towers. That you construct by taking a primary state and acting on it with Fourier modes of the stress tensor. And I forgot a very important piece of information, which is that let's do that. Let me me just say what I forgot. So I forgot to say this. Maybe at this point you might be confused by that. I forgot to say that Ln acting on primary state phi, this is 0 if n is positive. And I will explain quickly why this is so. Was there a question? Yes. Well, that's our definition of the field phi. If you want to put the field not at the center, then it will. You can do that. You could indeed consider a state. You can. That's an interesting question, actually. Exercise. Thank you for suggesting this exercise. So exercise. Write the state that would correspond to this. So this is the origin. And let's insert a field phi of z here. Write this state, but write the state in this algebraic formalism. So what does it mean? Write the state. Write the state as a sum of terms of as a sum of terms of this form phi with some coefficient plus all the descendants plus gamma L minus 1 squared times phi, plus delta lambda minus 2 phi and so on. This you can do. Do you see how to do it? No? Well, you see what you need to do is what is this state? This state is the same as taking phi at the origin and translating it by vector z. So you have to think about how to write a translation in that language. But it turns out the translation operator, you have to think a bit about it, but translation operator turns out to be L minus 1. So in fact, a translation by a vector z, you would write this as exponential z L minus 1. Possibly with a minus here, and this I'm not so completely sure, but it has to be of this form. And so the result here should be of the form e exponential z L minus 1 acting on phi. Okay. But the convention is just to put the primary at the origin, and then this defines the state phi. Okay, now why is this true? Why do the positive modes of the stress tensor annihilate all the primary states? This is because this is a consequence of this OPE here, of this operator product expansion. So you have to look at what is the definition of this thing. The definition is contour integral of dz. So this is a contour integral that encircles the origin of zn plus 1. And by definition, this is zn plus 1 times t of z times phi at the origin acting on the vacuum. So phi at the origin acting on the vacuum, that by definition is the state phi. Now and so by definition Ln is this. Now here you can use the operator product expansion. So here you use the operator product expansion. And you see that this gives you delta over z squared phi 0 plus 1 over z d phi 0 plus regular terms. But you see that since you are multiplying this by z to the n plus 1 with n positive, or n larger, n 0 or strictly positive, n is strictly positive here, you see that this kills the pole. And so there are no poles left, and so this is 0, as claimed. Okay. this is 0. So you see, there's a direct correspondence. I mean, you have to get used to it, but there's a direct correspondence between these algebraic manipulations of the modes of the stress tensor and the operator product expansion. Okay, and finally, the last very important thing that I want to say is that there's an inner product naturally defined on this Hilbert space. So there's an inner product. And the inner product, how do we define it? Well, we want, you see, we want for a state like this that would correspond to, again, some insertions of some fields, phi1, phi2, phi3, possibly insertions of the stress tensor at some point. So for a state that we would generate in this way, taking the disk and throwing some operators inside, that would be a state in our space. We want, okay, the drawing is going to be difficult, so let me just put less points. Let's just put 2, phi1, phi2. So I want to define an adjoint. So I want to define what is this dagger symbol. So how do I define this dagger symbol? Well, we're going to define it as this. So we're going to define a ket. And the ket, in order for these things to make sense, we would like the ket to correspond to, the complement. So instead of integrating degrees of freedom inside the disk, now we want to integrate them outside. Like this, and the positions of the points, we want to take them at the mirror images across the disk. So this we're going to put here. So if this is phi1 of z1, this is going to be at phi1 of 1 over z1 complex conjugate. And this phi2 is going to show up here, phi2 of 1 over z2 complex conjugate. So why do we do this? Because then this makes sense, because then we can compute things like that. The inner product between a state that would correspond to this, integrating out all these degrees of freedom with insertions of, for instance, some fields phi3, phi4, and this guy here with some other insertions, phi1, phi2. We want this to be, the correlation function in the full plane, where now we have integrated everything out, and we have some fields phi1, phi2, and phi3 here. Phi1, phi2, phi3, phi4. Okay, so that's what we want about our inner product. That's what we want. We want it to do this. So it's now not difficult to see from the definition of both those primary states and the Fourier modes of the stress tensor that this is encoded algebraically as follows. So this rule is encoded algebraically as follows. So first, the inner product between two states, phi1 and phi2, this has to be delta phi1, phi2, so it's zero unless it's the same operator, the same primary operator, so that's for phi1 and phi2 are primary here. And second, Ln dagger is L minus N. So this I will not show, but it follows from the picture. Okay, so this is very important again, and so this is part of the general algebraic structure. So we have our fields that satisfy this inner product. This is delta phi, so it has to be the same operator, otherwise it's 0. And the adjoint is defined as this. Okay? So that's about it. About the algebraic thing. There's just one. Okay, so you can look at the commutation relations. Of the stress tensor, of the modes of the stress tensors, so of these LNs, of the Virasoro, okay, so they are called Virasoro modes because we find that the commutation relations are the Virasoro, given by the Virasoro algebra. So you can, from the definition and from this operator product expansion here, this one, you can check. It's an interesting exercise. But this, again, this is completely standard. You can find it in any textbook. You can find that the commutation relations of these modes is given by n minus m, L n plus m, n plus m. Plus c over 12. This term is coming from here when you do the calculation. C over 12 n squared minus 1. Delta n plus m, 0. That's called the Virasoro algebra. It's just the algebraic way of writing this operator product expansion. Okay, so there is a Virasoro algebra where the central charge shows up. Okay, so that's what there is to say, and so this specifies this algebraic perspective on the theory. And now this is what can be said in full generality. So in full generality, there's not much more that you can say. So if we want to say more, you have to enter the details of some specific theories a little bit. So you're no longer doing conformal field theory in full generality, you're entering details of specific theories. So in some specific theories that were discovered in 1984 and that were very important in terms of fundamental physics are the minimal models. I will focus only on the, well, let's say just minimal models. Minimal models, and they came up in a very important paper. In my opinion, in anybody's opinion, one of the most important paper in theoretical physics in the 20th century, probably, because it was really a big breakthrough for fundamental understanding of phase transitions in 2 dimensions. So, okay, so you can look at this paper. It's a fantastic paper by Belavin, Polyakov, and Zamolodchikov. And so what these people did is that they started from there, started from the knowledge that there was a Virasoro algebra, and they realized that, so it was known that So the representation theory of the Virasoro algebra was known to some extent, and they used this to find some specific models that have some important property. So this follows. Let's look back. Let's have a quick look back at the inner product. Quick look back at the inner product in our CFT. So the problem is that there is a problem, which is that it's not, or maybe it's a problem, maybe not, but it is a fact that it's not necessarily positive definite. It's not necessarily positive definite. Which means what? Which means that you can find sometimes states that have a negative squared norm. So one example, for instance, simple example is this one. So you can consider this linear combination of two states, L minus 2 acting on some primary field phi and L minus 1 squared acting on some primary field phi. Why this specific combination? Because they have the same conformal dimension. So it's better to look at things with the same conformal dimension. This ensures that they have a non-zero inner product, because fields with different scaling dimension, different conformal dimensions would automatically have a zero inner product. This follows from the definitions. So this squared norm, okay, you can compute using the commutation relations of the Virasoro algebra, and let me just give you the formula. Okay, so you see this will be a sum of three terms. This minus 2 alpha phi L2 L minus 1 squared phi plus alpha squared phi L1 squared L minus 1 squared phi. This is phi, sorry, here. You can compute these three things using the Virasoro algebra. I'm not going to write it down. The result involves delta, so this is some function of some expression that involves alpha, delta, and c, and it can be negative. In some for some of choice of these parameters. For some choice of these parameters. So is this a problem? Sometimes it is, sometimes it's not. It depends what you want to do. So it depends what you have in mind and what your conformal field theory is supposed to describe as a microscopic, in terms of the microscopic system you're thinking about. So for instance, yesterday we talked about percolation. Percolation is a theory with central charge 0. You can easily check that in a conformal field theory with central charge 0, with this definition of the inner product, there's only one state in the entire theory that is properly defined with positive norm. That's the vacuum, and then all the other states, they have zero norm, so you can quotient them out. So does it mean? And this is related to the fact that the partition function is 1 in that theory. So does it mean that the theory is not interesting? No, it doesn't mean that. It just means that the theory doesn't have a positive definite inner product. But you have to work with this. You have to live with this. So when there is no positive definite inner product, one talks about the non-unitary theories. But then what these people did is that they understood that It was important to stress unitarity of the theory, so to ask for a positive definite inner product. If you want to make the identification of your conformal field theory with models coming from statistical mechanics, classical statistical mechanics with local and positive weights, such as the Ising model or the Potts model, or all these things. And so they insisted on unitarity, and it turns out that if you focus on theories with center charge smaller than 1, there exists a discrete family of conformal field theories that are unitary, so that have a positive definite inner product, and these theories are labeled by an integer p, larger than 2, say, and they have a central charge that is given by 1 minus 6 over p plus 1. So only for those specific values of the central charge you can have a conformal field theory that is unitary and has conformal dimensions 1. It's not possible otherwise. And moreover, the scaling dimensions, there is a finite number of primary fields in these theories. So there's a finite number of primary operators in those theories, and their scaling dimensions is given by this formula. Delta Rs is p plus 1 times r minus p times s squared minus 1 over 4 p plus 1. And here r is between 1 and p minus 1, and s is between p and 1. This formula is known as Katz's formula. So by insisting on having a positive definite inner product in the theory, quotienting out the states that have zero norm and so on, so there's a lot of algebraic thing that's going on there that I don't have time to go into. If you're interested, this is well explained in these lecture notes by Ginsberg, for instance. It's nicely explained in a concise way. So you can have a look there. But basically, by insisting on having unitary theories, then you severely restrict the possibilities. And if you look, so I would have liked to explain this in more detail, but I will not have time. So if you look at the first few examples, well, so first, it's trivial, but let's just do it. So what is p equals 2? What would be p equals 2? P equals 2, you see that the central charge would be 1 minus 6 divided by 2 times 3, which is also 6. So this is a theory with central charge 0. And you can also check that there's only one primary field in that theory that's delta 1, 1, that has also dimension 0. So in fact there's only one state in the theory, only one state with non-zero norm, with non-zero norm, and this is the vacuum itself, which has norm 1. All other states they go away if you insist on unitarity. So this is a trivial case, trivial, and there is nothing interesting to say about it. But now if you look at p equals 3, plug p equals 3 into these formulas, and then you find that c equals 1/2, okay, that's already less trivial, and you find that there's this table of delta rs with, okay, that's 3 columns, like this, here for s equals 1, s equals 2, s equals 3, r equals 1, and r equals 2. You can compute the dimensions, and you'll find that there's one that has dimension 0. Okay, fine, that's the vacuum. The vacuum always has dimension 0. Conformal dimension 0, and then there's one with conformal dimension 1/2, and one with conformal dimension 1/16. And the table repeats itself, so it's symmetric. So here it's also 0, and here it's also 1/16, and here it's also 1/2. But that's just a trivial symmetry of the table. So we should not view these operators as independent. So let's just remove those possibilities from the table. Okay, so what does this tell us? It tells us that this is a theory that has a vacuum, that has the identity as a primary. Identity is always a primary operator, so that's not the interesting one. But apart from this one, it has two primary operators with conformal dimension 1/2 and conformal dimension 1/16. Conformal dimension is half the scaling dimension, so we see that this theory has two operators, one with scaling dimension 1, 2 times 1/2, and one with scaling dimension 1/8. Okay, and so now if you know some statistical physics and if you have taken a course in phase transitions, you know that the phase diagram of the Ising model is a two-dimensional phase diagram. So around the critical point of the Ising model, if you have the Ising model like this. This is a function of the magnetic field and the temperature. There's a critical point here. And so around this critical point, you can work out the renormalization group flow. It looks like this in that direction. So this means that, and then it looks like that around here. So this means that around this critical point, there are two relevant perturbations. One corresponds to temperature, one corresponds to magnetic field, and you can identify them with those two primary operators that are relevant with scaling dimension 1 and 1/8. And you can play this game with the other minimal models. So the next one with p equals 4 has central charge 7/10, and it has, let me check, 4 primary operators, I think, if I remember correctly. It's in the notes somewhere. Yes, it has 4 relevant primary operators. It has 5 primary operators, but only 4 of them are relevant. There's one that is irrelevant, and this you can identify with the tricritical Ising model. The p equals 5 model, you can identify with the Potts model, 3-state Potts model, and so on. And so in general, the whole series of minimal models has been identified with an infinite family of classical stat-mech models that is known as restricted solid and solid models that were constructed by Baxter and collaborators. Baxter, Andrews, and Forster. So when these ideas came up in the 80s, people already knew the candidates for this family of critical points, and then they play the game of identifying them with stat-mech models. Okay, there's much more to say, but we don't have time for this, so I'll stop here. Yes, the vacuum would be the same. No, in general, it's a correspondence, so you have to know both in a lot of details to be able to make them, in order to be able to be sure that they match. So it's no, there's no recipe to take a lattice model and just figure out what's the correct conformal field theory. I mean, what you can do is okay. So one thing that people do a lot is you take the transfer matrix of your stat-mech model. So it's a 2D stat-mech model. You view it as a sort of a one-dimensional model that evolves in imaginary time. It's evolved by the transfer matrix. You can do numerics on this. You can find the spectrum of the transfer matrix, and you can match the spectrum of this transfer matrix with those states. So this is a relatively concrete thing that you can do. But still, it requires a lot of work and a lot of analysis, and it's not like you push a button and your computer tells you it has to be this conformal field theory. But accessing the sample charge, for instance, is relatively easy. Because as we discussed in lecture 3, if you are a critical spin chain, for instance, the central charge you will get very easily by doing TMRG or ITBD or whatever, and it would give you the entanglement entropy. The entanglement entropy tells you what the central charge is. In a classical stat-mech model, you would take the transfer matrix and look at the largest eigenvalue of the transfer matrix, and this will also contain the central charge. So the central charge is usually easy to tell, but then going beyond central charge is not necessarily very easy. Mm-hmm. Mm-hmm. Not that I know of, no. Just some label. I mean, it has some sort of meaning in the. Okay, these models can be represented in terms of the Coulomb gas that we discussed yesterday. So, in terms of a absent free field where you put some charges to make things work, some charges, for instance, at the endpoints of a long cylinder, as we did yesterday, to make things work. And if you do that, then this R and S have some meaning in that construction. They correspond to something called magnetic and electric charges, for instance. But in general, from that perspective, I don't think so. It's just coming out of some algebraic constraints. If you want to know more about this, read Ginsparg's lecture notes. Okay, thanks.